In this we are going to solve the non-homogeneous differential equation. So we're going to solve the non-homogeneous differential equations. So there are not many techniques available to solve the non-homogeneous equation. So out of the methods available, there's a method called the Undetermined Coefficient Method. So we can discuss that in this discussion. So what we call Undetermined Coefficient Method. Undetermined Coefficient Method. So under the Undetermined Coefficient Method, we can handle three type of differential equations. We can talk about that later. So let's discuss how the method works. So let's say so we consider a problem like this. So let's say so consider y double prime plus 5y prime plus 6y equals to, let's say, 2x plus 1. So you can see that on the right hand side it is not equal to 0. There is there's a function there. So we call these kind of equations non-homogeneous equations. So non-homogeneous differential equations. So there is a function on the other side. It's not equal to 0. So if you get a problem like that, so we normally call this part is like, let's say, fx, some function. So what we're gonna do, we're gonna break this problem into two parts. We're gonna consider the homogeneous equation associated with this. So that means in this case it is y double prime plus 5y prime plus 6y equal to 0. So this is the associated homogeneous equation. So what we're going to do, we're going to find the general solution of the homogeneous equation. We're going to find the general solution for this part. So what we're going to do, we're going to find the general solution. So find the general solution. Solution of the homogeneous equation. So we're going to find the general solution of that, and this solution is sometimes called the complementary solution. It's called the complementary solution. So because of that, we normally call this is YC, because that's the complementary solution. What's the complementary solution? The general solution of the homogeneous equation. Then what we're going to do, and we're going to find just one solution to the non-homogeneous equation. So we're going to consider that non-homogeneous equation again. That's the original equation. So we're going to find just one solution. So one solution is enough. Just one solution to this part. That's what we normally call the particular solution, like special solution. So we're going to find a particular solution, just one solution. Particular solution. We're going to find a particular solution to the non-homogeneous equation. Find a particular solution to non-homogeneous equation. So we call this is the YP. And then there's a theorem which says that the sum of these two gonna give you the general solution to the non-homogeneous equation. So it's very powerful result. So it says that then if you add the two, then the general solution to the non-homogeneous equation is simply the sum of the two, YC plus YP. So it's a very powerful result. So what we need is, again, we're gonna find the general solution to the homogeneous equation. We're gonna find a solution to the non-homogeneous equation, we add the two, then it's going to give you the general solution to the non-homogeneous equation. So let's prove this result, because it's a very powerful result, and proof is not that difficult. So we're going to prove that result first. That's the major result of this discussion. So theorem. So we're going to give this as a theorem. So what it says that the general solution to the non-homogeneous equation is yx, which is yc plus yp. So what is yc? Because it's a second order differential equation, so it's going to look like c1y1 plus c2y2 plus the yp. So, and then it says that this is a general solution to the homogeneous equation. So where we can say where y1 and y2, where y1 and y2 are two solutions to a linearly independent solutions to the homogeneous equation and yp is a particular solution. Yp is a particular solution. It's a particular solution to the non-homogeneous equation. Good. So, so in this one, so the method applies whether it is a constant coefficient or not. So this, so it doesn't restrict only to constant coefficient equation. It can be like even like, you know, for example, Euler-Cauchy differential equation type of problems. So any second order differential equation, but if you can find the general solution, just add that to the particular solution and then you get the general solution. So let's see how we can prove this. So this is like a powerful result. So we're gonna prove this. But we're gonna prove this through a another theorem. So we have another theorem. So what that theorem says, let's look at this one. So it says that if y1 and y2, if y1 and y2 are any two solutions to the non-homogeneous equation, are any two solutions and any two solutions to the non-homogeneous equation, any two solutions to the non-homogeneous equation, then the difference y1 minus y2 is a solution to the homogeneous equation. So what it says, so if you can find two solutions to the non-homogeneous equation, and if you take the difference of the two, it's going to be a solution to the homogeneous equation. And we're going to prove this result, because from this result we can get the other one. So let's prove this result. So what we can do, we can assume a differential equation first. So so let's say we have a differential equation of this form, a y double prime plus by prime plus cy equal fx. So ABC can be some functions of the independent variable also, so we don't restrict about that. Now what we can do, since y1 and y2 are two solutions to the non-homogeneous equation, what you can do, you can plug in that. So that means it should satisfy the equation. So we're going to get a y1 double prime plus b y1 prime plus cy equal fx, because it's a solution of the first equation. We can do the we can write the same thing with the second one. So we can say no, that's not right. So this is y1. So same thing with the second solution. So you can write a y2 double prime plus b y2 prime plus cy2 equal fx, because those two are solutions to the non-homogeneous equation. Now what we're going to do, we're going to subtract them. So by subtracting, if you subtract them, so if you subtract them, what's going to happen? It's going to be a y1 double prime minus y2 double prime plus b y1 prime minus y2 prime plus c y1 minus y2 equal fx minus fx is 0. So now what we're going to do, so you're going to see something. For example, you can see what is inside the parenthesis is just the difference between y1 and y2, and first one is the second derivative and the first derivative and now derivative. So what we're going to do, we're going to define that as y2. What we're going to do, we're going to define this part as y. Okay, so let's do that. So let's say let y equal y1 minus y2. So if you say y1 minus y2, now what you can see is, then you can take the derivative, so you're going to say y prime becomes y1 prime minus y2 prime, and y double prime becomes y1 double prime minus y2 double prime. So that means we can plug in that to the equation. Once you plug into that to the equation, then I'm going to call this star, then star becomes a y double prime plus b y prime plus cy equals 0. In other words, this means that y is a solution to the homogeneous equation. So therefore y is a solution. Y means the difference between the two, that's the y, is a solution. Y is a solution to the homogeneous equation. So that's a very interesting result. So that means since y is a solution to the homogeneous equation, it may be equal to the general solution of the homogeneous equation, because it's just a solution. So any solution you can write it like that. So if you take the difference, it's going to be a solution. That means you can represent that by the general solution, because it's a solution. So now let's consider that fact. So that means what we can do now is the interesting part. So what we can do, because we know that the difference is always a solution of the homogeneous equation, that means you can use the general solution of the homogeneous equation to get that. So let's talk about that. So that means we can write the y1 minus y2 as the general solution of the homogeneous equation, but that we normally call yc, the complementary solution, because we know that this is a solution to the homogeneous equation, but the general solution is the complementary solution. We can set it equal to that. Now what we can do, we have a choice. So let's say, because we know that y1, y2 are any two solutions to the non-homogeneous equation, how about we're going to pick the first one as the general solution to the non-homogeneous equation? We're going to make a choice. We're going to say, okay, so this is the general solution to the non-homogeneous, because we can pick, because it doesn't matter, just two, and then we're going to say this one is a particular solution to the just one solution, so we can pick this one as the yp. So that means, in other words, what you get is this result. So that means you can solve for we can move y to the other side, so that means this can give you y. The general solution is simply going to be yc plus yp. So that is the result we were talking about. So that's the result we were talking about. So that means y is simply given by the sum of the complementary solution of the particular solution. So it's simply the sum of the complementary. So that's the complementary solution. And this is the particular solution. So now we already know how to find the complementary solution or the general solution to the homogeneous equation. That we know. So the only thing that we don't know is how to find the particular solution. So that is the focus of this discussion now. So let's ask this question. So how to find the particular solution? How to find the particular solution? Particular solution yp. So that's the goal of this discussion, how to find this particular solution, because after we know another particular solution, just add the two, you get a general solution. So we can talk about two different techniques. The first one is what we call the undetermined coefficient method. Undetermined coefficient. Undetermined coefficient method. And then the second one is what we call the variation of parameters method. Variation of parameters. We can discuss the variation of parameters in a different discussion. So let's talk about the undetermined coefficient method. So with the undetermined coefficient method, we can solve only three types of differential equations. So let's talk about that more. So undetermined coefficient method. Undetermined coefficient method. Undetermined coefficient method. Undetermined coefficient method. So under this technique, we can solve three types of differential equations. So if fx has these three types, so one type is e to a function, like exponential functions, and then it can be a sine cosine function, sine some number, or cosine some number. And the third type is a polynomial. So if you have a polynomial, like for example a t to the n plus b t to the n minus 1, like that. It can be any variable, it doesn't matter. So those are the three types that we can solve using the undetermined coefficient method. So what we're going to do, we're going to do one by one. So let's start with the easiest one, that is the exponential function. So we're going to start with that. So let's go to case 1. So case 1, exponential function. Exponential function e to the lambda x. So let's start with the problem. So let's say find a particular solution to y double prime minus 4y prime minus 12y equal 3 e to the 5t. So t is the independent variable. So I'm going to call equation number 1. Okay, so once you get a differential equation like that, this is the argument. We know that if you assume that your solution is another exponential function e to the 5t, so what's going to happen? We know that when you take the derivative, e to the 5t stays there. So only the coefficient is changing. So that means there is a chance that you take repeated derivatives and you plug into the left hand side, and you can simplify that side so that you can match the coefficient on the other side. So that's the goal. So what you're trying to do, you put an undetermined coefficient in front of it and you take the derivatives and plug in there and you simplify so that the two sides of the coefficient match each other. So that's the goal. So let's do that. So so we're going to say assume a solution of the form yp a e to the 5t. So you're going to put the exact same number here, a e to the 5t. So we don't know a. So we assume that is a solution. It's a solution to the non-homogeneous equation. So that's the undetermined coefficient. The a is the undetermined coefficient. The goal is to find it. So what do you do? Take the derivative. So we're going to take the derivative. So yp prime. If you take the derivative, so it is 5a e to the 5t, and then yp double prime, which is, you take it another 5, so 25a e to the 5t. Now what we can do, we can substitute. So substitute this into 1. So substitute to 1. So you can substitute to 1. Once substitute to 1, what are you going to get? So y double prime, that's going to be 25 a e to the 5t minus 4 times the derivative is 5a e to the 5t minus 12 a times e to the 5t. Equal, on the other side what you have is 3 e to the 5t. So let's simplify this side. Once you simplify this side, how much you get? You have 25, you have 20, that means 5, and then minus 12, so negative 7. So you're going to get negative 7a e to the 5t equal 3 e to the 5t. So only way this is possible is you're going to match this term to the other side. So just match the two. So that means this implies that negative 7a has to be equal to 3. In other words, a is, if you divide, negative 3 divided by 7. That's what you get. So that means we find that undetermined coefficient. So it has to be negative 3 over 7. So that means, so the particular solution is, solution is yp equal negative 3 over 7 e to the 5t. So that's the particular solution. So it's not that bad. So these kind of problems we can solve very easily. So you assume a solution of the form. So you assume a solution of the form and then take the derivatives and plug in, and then you're gonna equation, and then you try to find the undetermined coefficient there. So good. So let's try to solve a like complete problem, like a complete initial value problem. So let's see how things gonna work. So I'm gonna modify this question. So let's say we have a problem like this. So example, so let's say we have solved the initial value problem, y double prime minus 4y prime minus 12y equal 3e 5t, along with y0 equal 18/7 and y prime 0 equal -1/7. So let's see how we can solve this problem. So if you get a problem like that, normally what we do is, the first thing to do is to find the complementary solution. So so the answer, so find the complementary solution. So first find the general solution to the homogeneous equation. Y double prime minus 4y prime minus 12y equals 0. So how we do that? We can look at the characteristic equation. So the characteristic equation is lambda squared minus 4 lambda minus 12. This is easy to factor, so it is lambda, so it is 12, 6 times 2, so larger one get the sign here, that means 6 and 2 equals 0. So this says that lambda equal -2 and 6. So then the complementary solution, so the yc gonna be c1 e to the -2t plus c2 e to the 6t. So that's the first one. So you find the complementary solution. Now what we can do, we already know what is the a particular solution. If you don't know the particular solution, now we're going to find the particular solution, but since we know it, we can write it, and we know that yp is equals to -3/7 e to the 5t. So when you get a problem like a general problem like that, we always find the yc first for a reason that will be clear later, and then find the yp. So since we know this one, so the general solution to the IEP, so the general solution so the general solution to the initial value problem is, it is simply the sum of the two, yc plus yp, which is c1 e to the -2t plus c2 e to the 6t minus 3/7 e to the 5t. After we get this general solution, then you're going to use the initial condition to find c1, c2. So you have to be careful. So the hint is, use the initial condition at the end. So it's kind of go backward. So so I'm going to put a star here. So use initial conditions at the end. So even though we call the initial, we can use that at the end. So this is the kind of way to remember that. So use the initial condition at the end. So now we can use the initial conditions to find c1, c2. So let's use the first condition, which says that when you plug in 0, you should get 18/7. So we can use that. So we can use using y0 equal 18/7. So we can write 18/7 equal, so let's plug in 0 to the equation. So we're going to have c1 e to the 0 plus c2 e to the 0 minus 3/7 e to the 0. So if you simplify, what are you going to get? So you can see that you have c1 c2, and if you bring this 3 to the other side, it's going to be 18 plus 3 means 21 divided by 7 means 3. So you have 3 equal c1 plus c2. So that's one equation. And then what we can do is we can take the derivative of the differential equation. So taking derivatives, taking the derivative of the solution, we can write as y prime t equals negative 2 c1 e to the negative 2 plus 6 c2 e to the 6 t minus 15/7 e to the 5t. Now what we can do, we can use the other condition now. So then using y prime 0 equal negative 1/7, so we can write this equation. We can write negative 1/7 equal negative 2 c1 plus 6 c2 minus 15/7. Now what we can do is, again, we can bring this to the other side. Once you bring this onto the other side, what will happen? 14/7. 14/7 means 2 equal negative 2 c1 plus 6 c2. You can divide this one by 2, so you're going to get equation 1 equal negative c1 plus 3 c2. Now the question is, what is the fastest way to solve these two equations? So what I normally do is, you're going to add the two, because you're going to see one plus coefficient, one minus coefficient. So when you see plus minus coefficient, the best thing, see here the coefficient is plus 1, here the coefficient is minus 1. So when you see plus minus like that, the best thing would be just add the two, because that term going to get cancelled out. So then you can see that by 1 plus 2, if you add the 2, you're going to get 4 equal 4c2. This says that c1 equal c2. This says that c2 equal 1, and if you plug in c2 equal 1 to one of those equations, you can see that c1 equal 2. Okay, so you get the two coefficients. Now you know the solution. So therefore the solution to the initial value problem is simply y equal 2e negative 2t plus e6t minus 3/7 e to the 5t. So that's the solution to the initial value problem. So you can see that that problem is not that difficult, but still there are some steps to follow. Very good. So that is the first type. So we find the particular solution first, and then so if you go back to the problem, so let's see what we did. So we try to solve this problem first, try to find the particular solution. So what we do, we look at the non-homogeneous part, and you're going to see that e to the phi t. So since you have e to the phi t, you assume a solution of the form a e to the phi t, a e to the phi t, and then the goal is to find a. How we do it? We take the derivatives first, you need the first derivative and second derivative, and then plug into the equation. Once you plug into the equation, you can simplify. Once you simplify, on the left side you're going to get negative 7a e to the phi t. On the other side you're going to get 3e to the phi t. You simply equate the coefficients. Once you equate the coefficients, you can see that -7 a equal 3, so a equal -3/7, and then that's going to give you the undetermined coefficient. So in this case it is -3/7, so the particular solution is simply going to be -3/7 e to the phi t. So that's how you find the particular solution. After that, we know what to do. We know how to find the general solution to the homogeneous equation. That's what we normally call the complementary solution. So we can use the same thing that we learned before to find. So that means we can do a problem like this. So if you want to do a problem like that, what we normally do is first we find the complementary solution. That's how we normally do it. First we find the complementary solution, and then after we find the complementary solution, then we find the particular solution. Since we already know the particular solution, we can use it right now. And then the sum of the two is the general solution to the homogeneous equation. So that's is simply given here. So that's the general solution to the non-homogeneous equation. So after we get the general solution to the non-homogeneous equation, what we can do, we can use the initial condition now. Okay, so you have to remember that. So you're going to use the initial condition at the end. So you're going to use the initial conditions. First we plug in the first one, just plug in 0 and e equal to 18/7, and then take the derivative and plug in, and then find, and then only thing is that you're gonna get two equations, just a set of equations. And what we do is we're gonna solve those two equations. You're gonna get one equation, 3 equals C1 plus C2. You get another equation, 1 equal -C1 plus 3C2. The best way to solve these two is when you see opposite signs. So the best thing would be to add them so that they cancel out, and then you simply get 4C2 equal 4. So that means C2 equal 1, and you can plug in that value to one of those equations. The first one is the easiest. You get the other value. Once you get the two values, you can plug in that there, and then you find the solution to the initial value problem. So this is the first type. So how to handle a exponential function. Let's talk about the second one. So second one is you're going to see either sine or cosine term. That's the second type. So let's talk about that. So the example number 2, find a particular solution to find a particular solution to so let's have the same equation, then you can see where what is actually changing. So I'm not going to change this part. Equal, let's say you have sine 2t. So it can be sine, cosine, or the sum of the two. So if you get a problem like that, this is the argument. You know that when you take the derivative of sine, it's going to give you cosine. And you can see that in the differential equation, you're going to see the y prime term there. So that means you cannot just assume a sine 2t in this case, because it's going to change sine to cosine. So what we can do, if you see a sine term or cosine term in the yp, in the undetermined form, you get the sum of the two. So that's how you do. So that means we can assume, so suppose yp equal not just one, the both of this, a sine 2t plus b cosine 2t. It doesn't matter what you can write first, but you have to write both. So that's what you need to remember. If you see a sine term, single sine term or single cosine term or both, you have to write both of them. So that's very important, because when you take the derivative, it's going to change from sine to cosine. It's not like before. So that is the particular form that you can assume. Now what you do, it's the same thing. Take the derivatives, plug in there, equate coefficients. So let's do it. So we can take the derivatives. So the yp prime is a sine. So you take the derivative, it's become cosine, but because of the 2 comes out. So that means you're going to get 2a cosine 2t. And then cosine, when you take the derivatives, we have negative sign, so it's a negative 2b sine 2t. And you can see the second derivative here. That means you have to find the second derivative as well. So if you take the second derivative, sine become cosine becomes sine with the negative sign, so negative 4a sine 2t, and here sine become cosine, so negative 4b cosine 2t. Okay, now what we can do, we can substitute. Okay, we can substitute. So there are two unknown now. Okay, there are two unknown. So let's try this. So there are two unknown. Okay, there are two unknown. Good. So let's substitute. So once you substitute, what do you get? So the first term becomes negative 4a sine 2t minus 4b cosine 2t. That's the first term, and then minus 4 times, plug in the derivative, it is 2a cosine 2t minus 2b sine 2t, and then negative 12, and we're going to plug in here again, but that's the original one, so it is a sine 2t plus b cosine 2t, which is equals to what is on the other side. Other side is sine 2t. Now what we can do, so this should satisfy. So your goal is to find a, b, so that this equation is satisfied. So what we normally do is we can equate the coefficients of linearly independent terms. So what are the linearly independent terms? Sine and cosine are linearly independent, that we know. So that means we're going to equate the coefficient of sine and equate the coefficient of sine and cosine separately. So so the coefficient of cosine, it doesn't matter which one. So coefficient of cosine 2t, because they are linearly independent. So what are the coefficient of cosine? How to get the cosine term? You're going to get a negative 4b. So I'm going to write that in red. So that is a cosine term. This is a cosine term. And then this is a cosine term. So let's write them. So you're going to get negative 4b minus, you have 8a, and then minus 12b equal, do you see any cosine term on the other side? There are no cosine term. That means the coefficient is 0. That's the interesting part. Do the same thing. So now what we can do, coefficient of sine, sine 2t. So let's do that. So this is a sine term, and there's sine term on the other side as well. So let's equate all of them. So it is negative 4a, and then plus, you can see 8. So when you multiply these two, you're going to get 8b, and then minus 12 a equal, what is on the other side? The coefficient is simply 1. So now the goal is to solve these two. So so just solve these two, but you can see that you can simplify this a little bit. So if you simplify, what do you get? So when you simplify, it's going to be negative 16b minus 8a equals 0, and the other one is 8b minus 16a equal 1. So so what you can do is just try to isolate one term. So what we can do probably is you can multiply the bottom one by 2, or you can actually divide the top one by 2 first, because once you divide the top one by 2, it becomes negative 8b minus 4a, and then you can add the 2 and you can solve. Okay, so this is like easy to solve. So so what I normally do is I divide the top one by 2, then it's going to be negative 8b negative 4a equals 0, and then you're going to add the 2. Once you add the 2, b term get cancelled, you can solve for a. So you can see that once you do that, you're going to get a equal negative 1 over 20. Now what we're going to do, we're going to substitute that value to the other one. So you're going to get b equal 140. Okay. So once you plug in that value, you're gonna see that b equal 1/40. So this is like very simple calculation. Okay. Good. So so since we know a and b, now we know the solution to the particular solution. Okay. So the particular solution is so the particular solution is yp equal a is negative 1/20 sine 2t plus 1/40 cosine 2t. So that's the particular solution, and then we can also write the general solution, just add in the yc term. Okay, good. So let's go to the third type. So this is the second type. When we see sine cosine terms, so let's go back. When you see sine cosine term, even though it's single term, you need to write both. The reason is, once you take the derivative, sine become cosine, and you can see that b is not equal to 0, b is 1/40, so that means it's there. Okay? It's there. So this justifies that that's actually the case. So let's go to the third case. So the third case is the polynomial. So case number 3, polynomials. So something t to the n plus something b to the n minus 1, like that, and then a constant term. Okay, so let's see how to handle this kind of problem. So let's look at an example. So let's say find a particular solution. Find a particular solution to y double prime minus 4y prime minus 12y equal 2t3 cube minus t plus 3, something like that. So y double prime minus 4y prime minus 12y equal to t to the cube minus t plus 3. So if you get a polynomial, things are easy. What we normally do is we can write as a polynomial of the same type, but you're going to include all the missing terms. For example, you can see that here there is no t squared term, but you have to include that. So the answer, suppose yp, what we can do, we can include all of them. So it is a t cube plus b t squared plus ct plus d. So that means there are 4 unknown for this problem. 4 unknown. So it can be a little complicated because they're going to get 4 equations, but what we try to do, we try to find as much as we can at the beginning so that you have just few things to find. So as before, take the derivatives and plug in. So yp prime is 3a t squared plus 2bt plus c. So one term is gone, and then yp double prime, which is 6at plus 2b. That's the highest derivative we need. Now what we can do, we can substitute. Okay, so substitute. In 3, so we're going to call this is 3 into 3. So we do that. So once you do that, so what do you get? So let's see term by term. So the first term simply becomes 6 a t plus 2b, that's the first term, minus 4 times the second term is 3a t squared plus 2bt plus c, that's the second term, minus 12 the last term, which is a t cube bt squared ct plus d, which is equals to whatever on the other side. Other side is 2t cube minus t plus 3. That's what we have. So what we can do, I remember we do it partial fraction method. We equate the coefficient of the terms with same degree, because those are the linearly independent terms. So what we are trying to do is we can equate the coefficient of linearly independent terms. Equate the coefficients of linearly independent terms. Same thing. So we can equate coefficients. Okay. So what we can do? So equate coefficients. So we can what we normally do is we can start with the largest power. Because once you start with the largest power, you can actually find many terms. So we can start with t cube. So if you start with t cube, that's the largest term. So where are you going to get the t cube term? You can see that this is the only t cube term that you can see on this side. So that means you can write negative 12a. So that's the coefficient, which is equal to, what is the coefficient on the other side? Simply 2. You can see that this going to give you the a value. So a has to be, if you divide by negative 12, negative 1 over 6. So you can see it's already there. We already know what is a. Now what we can do, the next term. So we start with the largest power always. It's going to make the calculation easier. So what's the next term? T squared term. So let's see where you're going to get t squared terms. So you can see there's a t squared term here. There's a t squared term there, and there's no t squared term on the other side. That means 0. So let's do that now. So let's start with the t squared. So you're going to get negative 12a. That's the first term. And then also get negative 12b. Negative 12b, which is equal to 0. So this says that you can see negative 12 and negative 12 you can cancel. It says that b equal negative a. So b is simply equals to negative a. That means this has to be equal to 1 over 6. So we only find the coefficient of the second term. Go to the next one. So we're gonna go with the t term. So what's the next term? Is t. So if we go to the next term, so let's see what are the terms that we're gonna see. There's a t term here. There's a t term there. There's a t term there. So we're gonna go with that. So that means you're gonna get, but we already know some of the values. So the best thing would be plug in the values that we already know. So it's gonna make the calculation easier. So I'm gonna start the first term. So it is 6 times a, but a is equal to negative 1, 6. So I'm gonna plug in those values. Negative 4 times 2, but negative 4, 2b. So negative 4, 2, and a b already know it is 1 over 6. So we're going to plug in that value here. And then minus, you're going to see 12c, that's the only thing we don't know, which is equal to, the coefficient on the other side is negative 1. So let's simplify this. You can see this is not that bad, so it's easy to solve. So once you solve, you can see that you're going to get c equal negative 1 over 9. Okay, you're going to get c equal negative 1 over 9. Now only thing that you need to do is find the d term. For that, what we're going to do, we're going to substitute t equals 0 in this equation, or find the coefficient of t to the 0 term. T to the 0 is the constant term. Or simply say substitute t equal 0. That's the same thing. If you substitute t equals 0, all the t terms going to go away. So you will simply get 2b plus negative 4c minus 12d equal plus 3. So it is 2 times b is 1 over 6 minus 4 times c is negative 1 over 9. We see we already found what is c, and then minus 12d equal 3, and then we can simplify this, and you're going to end up getting, I'm going to write the value, you're going to get negative 5 over 27. So that's the d value. Okay, so we get all three values. Now what we can do, we're going to write the solution. So the particular solution, is yp equal, it is negative 1 over 6 t to the cube 1 over 6 t squared negative 1 over 9 t negative 5 over 27. So those are the, you can see that none of them are 0, so everything is not equal to 0. Good. So this is the idea. So you can see that that's not that much complicated. So what we want to do is we want to consider the three cases. So again, so I'm going to tell you what we're going to do. So what we did so far was, so the first case, when we had 3e to the 5t, you assume a solution a e to the 5t, and the next one was you had a sine 2t term, so you assume a sine 2t plus b cosine 2t, and then when you have a polynomial, so you had a polynomial 2t3 minus t plus 3, so you assume a general cubic polynomial here, so at3 plus bt squared plus ct plus d. So there are 4 unknown, and you try to find those 3. Okay, so let's try to put all of them in a kind of table so that you can use the idea later. So I'm going to call the table of guesses. How about that? So let's call table of guesses. So what we're trying to find is, you're going to solve the problem y a prime plus b y prime plus c y equal f to the t function. That's the kind of idea, and then we assume that t is the independent variable. It doesn't really matter. T is independent variable. So so in the table, when we see ft, this is what you're gonna go for yp. So that's the kind of idea. So we can write that. So let's start with the first one. You might see something, just a number. So something e to the beta t. Okay, so something like that. So if you see something like that, your guess gonna be a e to the beta t. That's the first time. So e to the beta t, you can repeat, but you put an a in front. And then if you see these 3 types, what are the 3 types? A cosine something t, or a sine something t, or the sum of the two, a sine beta t plus b cosine beta t. For all these 3, we have one type. So the type is simply a cosine beta t plus b cosine beta t. So they are the same. So what you want to remember is, I need need both sine and cosine. Okay, so remember that. So you have to write both, because once you take the derivative, it's going to change the type. So that's why you have to include both types. And then the last type is what we say nth degree polynomial. You're going to see a polynomial of nth degree. So let's say nth degree polynomial. So if you see a nth degree polynomial, what's you're going to write is simply is a some constant t to the n, another constant t to the n minus 1, like that. So you can write everything. So it is a1 t plus a0. You can write all the terms, everything. So those are the three types. Okay, so this is the first type, the second type, and the third type. So unfortunately, those are the only three types that you can solve using the undetermined coefficient method. So if you see anything else, you cannot use that. You can use this method, but still this can cover a lot of cases. For example, if you see tan or secant or something like that, this is not going to work. So we have to use some other techniques for that. That's what we call the variation of parameters, that we can discuss later. Okay, so so let's put that in a note. So so note is so only consider these three types. These three types. So it's very important, these three types. And then what we're going to do, if you see a product, so here we assume that just like one term. How about you see there's a product of those two types? So if you see a product of those two types, what we can do, we can write the general term of the first type, general of the second type, and then multiply the two. So let's write it. So when there is a product, of these types, okay, when there is a product, what we can do, write the guessing form for each type, right? The guessing form for each type and multiply them. So that's how you do it. So you write the different terms and then multiply the two. So for example, let's do one example just to clarify what we're going to do. So this is the idea. So let's say find a particular solution to y double prime minus 4y prime minus 12y equal, let's say t e 4t. So you can see that there are two types here. So so there are two types. That's one type, and then you have another type. So what we can do, we can write the general form for each. So we can write the general form for this. It's a t, that's a degree 1 polynomial, so that means it has to be at plus b. And if you look at the next one, this is e4t, so this is ce4t. Now what you do, you multiply the two. So that means so the answer would be, so we're going to try yp, which is equal to the product of the two. So it is at plus b times ce4t. So but that's what you get by the theory. But there is an interesting thing here, because what you can do is you can see that you can multiply by this c both terms, this and that. So that means you can include c in a and b. So that means this term is not necessary. So you can ignore this term when you have unknown in every other term. Okay, so if you see there's unknown in each and every term, so that means you can ignore that term. So that means what we normally do is we can ignore c, because then you can ignore one of the unknown. That's make it easy. So so what we have is we ignore c term, so we only write at plus b e to the 4t. The reason is c is already included in a and b, so we don't need that. So we only need to find two unknowns. So that is what we normally write as the particular solution or the guessing form when you have a product like that. So this same argument works for many other cases later. So you can see that, so I'm going to write it here. So we don't need, okay, so no need this extra c, because it's already included in, so we can say contained in a and b. So that's the reason. So that means you don't want to put that extra c, because otherwise you have one more unknown. Now after we do that, it's the same thing. Take the derivatives, plug in there, solve for a and b. So so you can do that. So and then after this, what we can do, take derivatives, and plug in and solve for a and b. That's how we do. So it's the same thing as we did before, but only thing is how to find the guessing term. So that's the interesting part. Now there is a confusion. So there's another note. So what if this beta, or this in the solution, so let's go back, remember the beta in the guessing form. What if this beta is root of the characteristic polynomial? If beta is a root of the characteristic polynomial, this technique does not work. So let's see why that doesn't work. So when beta is a solution to the characteristic polynomial, to the characteristic equation actually, to the characteristic equation, or root to the characteristic polynomial, okay, to the characteristic equation, it creates difficulties. So let's try to see how to do this kind of problem. So the example, find a particular solution to y double prime minus 4y prime minus 12y, no change, but here we have 7e6t. I'm going to call this equation number 4. So you have y double prime minus 4y prime minus 12y equals 7e6t. Now you can see that, remember the characteristic polynomial, what are the roots you're going to get? 6 and -2. So 6 gonna match now. So let's see where the problem comes. Okay, what happened when this is the case? So let's assume, let's try to do the same way that we try to do. So let's look at the characteristic equation. So let's try to understand the difficulty here. So the characteristic equation is simply lambda squared minus 4 lambda minus 12 equals 0. So the factors are lambda minus 6 and lambda plus 2 equals 0. So that means the lambdas are negative 2 and 6. So we're going to have the yc equal c1 e to the negative 2t plus c2 e to the 6t. So you can see that e to the 6t is already a solution of the homogeneous equation. Homogeneous equation. So that means once you try to plug in, if you just assume that your solution is ae6t, once you try to plug in that to the equation, you can see that because e to the 6t is a solution, the left hand side of the equation going to be 0. So you're going to get a contradiction in this case. So let's see. Okay, so in this case, yp equal ae6t does not work. Since 6 is a solution, to the characteristic equation, since characteristic equation ae6t is a solution to the homogeneous equation. So what happened if you try to take the derivatives and plug in, you're going to get yp double prime minus 4yp prime minus 12yp is a solution to the homogeneous equation. So that means this side is simply becomes 0 because it is a solution to the homogeneous equation. Since this is a solution to the homogeneous equation, when you plug in the yp, what's going to happen? This side is 0. So that means if you then what happened then from the equation number 4, what we have is we have this one. So what's going to happen on this side, you have 0, but on the other side you have whatever term that you had 7e6t, and you know that this is not possible. Okay, so this is not possible, this cannot happen, not possible. So that's the problem. So if you try to assume that ae6t is the general is the particular solution, then you can see that once you plug in it there, it's a solution of the homogeneous equation. So the left hand side is automatically 0. On the other side you have something non-zero. That means this is not possible. This is never going to happen. So that means you cannot assume a solution of the form. So this is not possible. So let's write it. So this is what we say, impossible. So what we do to avoid this one, we need to create a solution which is linearly independent of those two terms. What are the two terms? We need to find a solution which is linearly independent of those two terms, but still close to e to the 6t. So what we do is we simply multiply by extra t. T is the independent variable. You multiply by extra independent variable. So let's write the idea. To avoid this, to avoid this, so we take a yp, we take a yp that is independent, to e to the 6t. The easiest way to do this is multiply by an extra t. So our first choice is t times e to the 6t. So what we're gonna do, we're gonna put a extra a in front. So that's what we do. You simply multiply by a extra t term. That's gonna solve the problem. Okay. So take in this case yp equal a, the unknown, t, the extra t term, and then e to the 6t. So that's what happened when you see the 6 in as a solution to the characteristic equation. So we're gonna add an extra t in front. T is the independent variable. Now it's gonna solve the problem. So but you might see why we don't wanna, why we did not write it like this. For example, why we did not write this on as c1 c2t times e to the 6t. The reason is, if you split this c1 e to the 6t plus c2t e to the 6t, you can see that for whatever constant, this term is simply gonna produce a 0, because you know that e to the 6t is a solution. So that means this term is useless. So because of that, we are not going to write that term. We only write the second term. That's why we only write t term, just the t term, the second term, because that term simply going to go away. Okay. Now after that, what we can do, we just follow the same thing. After you know the format, take the derivatives, plug in there, solve for a. Okay. So the same idea. So I'm just going to write it, but I will not do it just to save time. Now and after that, and proceed as before. First finding derivatives. First finding derivatives. First finding derivatives. First finding derivatives, and then plug in in and solving for a. So you plug in and solve for a. It's just the same thing. Only thing is, what is the format now? So that's the only thing we need to worry about. The rest is just the same. So that in this case, the general solution. So general solution takes the form y equal yc plus yp. Yc is c1 e to the negative 2t, c2 is negative 6t, and then you need to find that coefficient. That's the one you need to find, and t is 6t. That's Aeᵃ. So this one we need to find. Okay, just follow the same thing as we did before. We're gonna find. So this need to find. Good. And then after we do that, then we use the initial condition. That's at the end. Then use the initial condition. Then use the initial condition. So we need two initial conditions to find C1 and C2. So that's the way we do it. Good. So how about so let's talk about another case. So example. So let's say, how about you try to solve like y double prime minus 4y prime. I will slightly change the problem. 4y equal 3e 2 x 2t, because we use the t as a variable. Now, so what is the characteristic equation in this case? So let's discuss this one. The characteristic equation is lambda squared minus 4 lambda plus 4 equals 0. So that means lambda minus 2 lambda minus 2 equals 0. So that means lambda equal 2 and 2. So what is the yc now? Yc is c1 plus c2x, or not xt, c2t e to the 2t. Now the problem is, you can see that this t match with that, but also t e to the 2t is already there. That means we cannot do the way we just did. It's not going to work now. So that means what you can do, you add another t, extra t. Okay, so because if you plug, because t e to the 2t is a solution now. So that means if you just plug in, it's going to get 0 on the left hand side as before. That means it's not going to work. So you have to add another t. Okay, so good. So let's try it. You understand the argument now. We're going to find another linear independent solution. So note that in this case e to the 2t or t e to the 2t do not work. So instead we take yp equal a t squared. You put one more t there, e to the 2t. So that's what you do. You add extra t term. So you understand the argument. It's not that easy. If you need to find another linearly independent, the easiest one is you just add a extra t there. So it's t squared, because we already see t in the solution, t e to the 2t in the solution. So that's not going to work. So we add that. Okay, so we consider what's going to happen if you can see when you write the exponential form. This only happen with the exponential form. There's no problem with the sine, cosine, or there's no problem with the polynomial. So this only happen with the exponential term. So let's write it. Yeah. So this only happens in the exponential case. Exponential case. So it's not going to happen with the not with the sine, cosine, or the polynomial. Okay, but not with sine, cosine, or polynomials. Okay, so it's not, it's only with the exponential term. Okay, good. So let's talk about the next one. So what's the next one? So we talk about the single term, and then we also talk about what if there's a product. If there's a product, what we can do, we can write the general form, and then of each type, and then multiply. And we also consider cases where you can ignore extra multiplication terms. So the next one is, what if you have a sum of the functions? So let's consider that. So that's the next example. So consider y double prime minus 4y prime, let's say 4y prime plus 4y equal, we have a sum here. It's not just 1 but 2x plus e to the 3x, something like that. So let's go with x now. So it's just a different variable, so you have to be careful. So if it's x, you have to go with x. If it's t, go with t. So here the difference is, we're gonna see two functions now. We're gonna see two functions. We're gonna see fx function here. We're gonna see gx function. So the question is, what are you gonna do now? So there's an interesting theory which says that you can solve them separately. You can go with one non-homogeneous equation with fx, another one with gx, and then solve the two and add the two to get the solution. So that's the kind of idea, but there's a shortcut, so we can talk about the shortcut as well. And then let's talk about the theory part here. So we can rewrite this kind of equation with a linear operator, because you can say that you can say L equal d squared over dx squared, and then minus 4 d over dx plus 4. So if you write it like that, that's the linear operator. So if you use this linear operator, then you can write this problem in a different way. So let's say we can rewrite. Okay, so we can rewrite this using a linear operator. Linear operator L. So that means your problem you can simply write as Ly equal to x plus e to the 3x. Because why we do that? Just to explain the theory much faster. Good. So you can see that Ly is the homogeneous equation. We operate on y, so that's the Ly. Okay, so let's talk about some notations. So that means your differential equation you can simply write as Ly equal the sum of the two, fx plus gx, like that. So now what we can do, if you get a problem like that, we're going to consider these two problems separately. You're going to try to solve this one and that one separately. That's one, this is the other one. You're going to solve these two separately, and then you're going to add the two solutions that you get. You're going to solve them, you try to find the particular solution for each type, and then you're going to add those two solutions. So let's talk about that a little bit. So what we're going to do, we're going to consider Ly equal fx and Ly equal gx separately. So we're going to solve those two problems like just different problem, because that's what we did before just few minutes ago. So we can do that. We can solve fx, the first part and the second part separately, but there's a nice theorem. This theorem gonna help us a lot. So what the theorem says, consider Ly equal fx plus gx. What it says that if y1 is a solution, to Ly equal fx, and y2 is a solution to Ly equal gx. So you consider two separate problems, gx, then it says that the sum of the two, y equal y1 plus y2, if you add the two solutions, is a solution to the original problem, Ly equal fx plus gx. This is very easy to prove, and you all know how to prove this result, because since L is a linear operator. So let's look at the proof actually. So this is a so let's say proof. So what we can do, we can consider L y, but what is y? Y is y1 plus y2, but we know that this is a linear operator, so you can break this as Ly1 plus Ly2, because this is a linear operator, linear operator. Now we know that Ly1 equals what? Ly1 equals to fx, because y1 is a solution to Ly equal fx problem, and the Ly2 equals to gx, because that's a solution to the second one. So this is coming from the first one, and that is coming from the second one, because those two are the solution. So what this says? This says that Ly equal, that means y is a solution to the original problem. Okay, so this implies that y equal y1 plus y2 is a solution to Ly equal fx plus gx. So that means this theorem makes our life much easier. So what this says that you can simply consider those two cases just at the same time. Yeah, so this is a very important result. So let's do let's try to like clarify this one. So it's a very important result. Very important result. So let's try to look at a problem. So let's say solve so solve the solve y double prime minus 4y prime plus 4y equal to x plus e3x. So what we normally do in this case, we can consider them separately. We don't want to do like 2x separately and e to the 2x separately. So we don't want to do that. What we're going to do, we can write the general solution of those two at the same time. So it's ax plus b is the form for that. Now form for this is ce3x. What we can do, we can add the two and consider as a single form. That's what we're trying to do. So so let's write that. So we can write the forms of each and add the two and solve that separately, solve that as just one expression. So let's do that. So not we can solve this, we can solve this as two separate problems, as two problems. Considering Ly equal 2x and Ly equal e to the 3x, but you can see that it is much easier if you consider this as just one single problem, but it is easier to write yp as a combined form, it is easy to write yp as a combined form. So we can write yp like this. We don't do 2, we do ax plus b plus c e to the 3x. So what we did, we get the two separate forms and combine them into one. Now what we try and do, we consider this just as one expression, and then we try to find a, b, c. So that's the easiest way to do it. Now after we get the form, we know what to do. So that's the form. Okay, so we can write the separate forms and then combine them as one. Good. Now what we can do, just find, okay, so find a, b and c as before. Okay, it's the same thing. And then you can see that there are three linearly independent terms there. So you're gonna so we can say equate coefficients of the coefficients of e to the 3x, x, and the constant term, Or for the last one, you can also do substitute x equal 0. So that is the way to do it. So actually let's try to completely solve the problem. So it might take some time, but that's worth doing at least one such problem. So yeah, so let's do that. So I'm going to do that quickly. It's just one signal problem. Okay, so let's do the complete problem. But you can try this as a problem from there and see whether you get the same answer. So solve the IVP y double prime minus 4y prime plus 4y equal 2x plus e to the 3x along with y0 equal 5/4 and y prime 0 equal 4. So let's try to do it now. So I'm going to show you all the steps in the right order. What we normally do, we find the complementary solution first. That's the first one, because now you know the reason, because we don't know whether the exponential term has the repetition, because in that case you have to add extra x or t depending on what's the independent variable. So it can save you. So because of that, we're going to find the complementary solution first. So let's do it. So we can write the characteristic equation, so which is lambda squared minus 4 lambda plus 4 equals 0. This says that lambda minus 2 squared equals 0. This gives you lambda equal to 2. The repetition. So that means the yc has the form c1 plus c2x e to the 2x. But you can see that you have a 3 in the equation, so that means it's different. So that's good. So then the yp takes the form, yp equal ax plus b plus ce 3x, takes the derivatives, yp prime equal a plus 3c e to the 3x, and yp double prime, which is 9c e to the 3x. Now we can substitute. By substituting, you're gonna get, so let's substitute the differential equation. You're gonna get 9c e to the 3x minus 4 times the first derivative is a plus 3c e 3x, and then plus 4 times the original solution ax plus b plus c e 3x, which is equals to 2x plus e to the 3x. Now what we can do, we can equate the coefficient of linearly independent terms. Equating coefficients, of linearly independent terms. So we have, so I'm going to go with the so see whether you can find something first. So I'm going to go with the constant term. So figure the constant term. What are the constant terms you can have? You have negative 4a here, so negative 4a, and you see another constant term for b, and there are no constant on the other side. If you divide it by 4, this says that b equal a, so that's a good one, b equal a. And then go with the x term. So if you go with the x term, you see a x term there, so there's x term here and there's x term there. So just equate the coefficient. You can say that for a equal to, this says that a, which is also equal to b, equal 1/2. So we find a and b. Now we can equate the coefficient of e to the 3x. So what are the terms you're going to get? You get 3 terms. There's a 1 term here, there's a 1 term there, there's a 1 term there, and you can equate that to 1. So let's write it. So if you write the coefficient of e to the 3x, you're going to get 9c minus 12c plus 4c equal 1, and this simplifies very well, and you can see that c is equals to 1. Okay, so that means you're going to get the yp. So therefore the yp is, because we have abc, all three is a 1/2 x plus 1/2 plus e to the 3x. So that is what you get as the yp. So therefore the general solution is, so the general solution is given by so the general solution is given by y equal yc plus yp. So this is c1 plus c2x e to the 2x plus the yp. Yp is 1/2 x plus 1/2 plus e to the 3x. So we find the general solution. Then you're going to use the initial condition because that's the last step. Now we're going to use initial conditions to find c1 and c2. So let's do it. So let's take the derivative because we need the derivative also. So I'm going to take the derivative of this term. So is y prime is what do you get? You have to use the product rule. So if you use the product rule, you're going to get c2 e to the 2x plus c1 plus c2x to the 2 times e to the 2x, and if you get the derivative here, you get 1/2 plus 3e 3x. Now we can use the initial conditions. So we can use y0 equal 5/2. This is going to give you 5/2 equal, let's plug in 0 wherever you see x. So we're going to get c1 plus 0 e to the 0 plus 0 1/2 e to the 0. You can see that you can solve for c1. What do you get? You have so this is simply equals to c1 plus 1/2 plus 1. So this says that c1 is simply 1. Now we can use the other condition. So y prime 0 equal 4. So let's do that. So it is 4 equals, so let's substitute the second one. It is c2 plus 1 plus 0 times 2 plus 0 plus yeah, so what do you get? Yeah, so 1/2, it's not 0, so it's 1/2 so you get so 4 equal c2 plus c1 is 1, so I plug in that value here, 0, and then you have 2 e to the 0 plus 1/2 plus 3, and then you can see that you're going to get 2 plus 3, this is 5 and 5.5, so it is c2 equal negative 1/2 negative 302. Okay, so we have the c2 value, so therefore the general solution is, general solution. So therefore the general solution is, so the general solution is y equal 1 minus x e to the 2x, actually not 1 minus x, it is different now. So you're going to get 1 minus 3/2 x e to the 2x plus 1/2 x plus 1/2 plus e to the 3x. So that is the that's a solution to the initial value problem. Okay, that's a solution to the, it's not the general solution, that's just a solution to the initial value problem. Okay, to the IVP. Good. So it's not difficult, but there are some algebra that you need to carry out. Perfect. So let's just do one more example from kind of different types, how it can work. So these are just extra examples. There's no new theories here. So let's do a problem like this. Write down the form of the general solution. So write down the form of the general solution. Okay, so write down. When you say write down, you don't want to give the explanation for that. You just need to write the answer. So write down the form of the general solution. So when you say find, that's a different question. Then you need to kind of explain everything. But when you just write down, just you can write down. So write down the form of the general solution. General solution. And asking just the form. So start with A. Y double prime minus y prime minus 6y equal e to the 2x. So the best thing would be look at the characteristic equation. So it is lambda squared minus lambda minus 6 equals 0. What are the factors? Lambda minus 3, lambda plus 2. So that means lambda equal negative 2 and 3. You can see that is not equal to any of them. So you can write the solution here. Simply y equal c1 e to the negative 2x plus c2 e to the 3x. So you can see the yp is going to be yp is going to be, because it's not equal to, so it's just a e to the 2x. So that is the form, because it's not equal to any of them. So number 2. Let's do another one. How about y double prime minus y prime minus 6y equal 4e 3x. Now the problem is this 3 gonna match, so that means you have to add a extra x in there. So in this case y is simply c1 e negative 2x, no problem, c2 e 3x, no problem, but now it's gonna match, so that means you have to add a extra x e 3x to find a linearly independent solution. Good. The next one. So how about y double prime minus y prime minus 6y equal 5 sine 3x. So when you have sine, it doesn't really matter whether this match or not. So what you're gonna do is you just write the way you write it, and also add the extra term. Let's say minus 2 cosine 3x, like that. So you can see that these two numbers are the same. So that means just one form works for both. So let's write it. So what's going to happen in this case is this side is still the same. You can see I did not change the homogeneous part, so that's why we are using the same characteristic equation. So the solution gonna be y equal c1e negative 2x c2e 3x plus a cosine 3x plus b sine 3. It doesn't matter which one you write first, but you can see that you don't need 2 because it's gonna cover both. It's gonna cover both of them. You don't write 4 terms, no. And the next one, d y double prime minus 4y prime plus 4y equal e to the 2x. Differential equation change, so let's write the new characteristic equation. It is lambda squared minus 4 lambda plus 4 equals 0. This is lambda minus 2 squared equal to 0. That means lambda equal to 2. But unfortunately that's exactly match with that. So what's gonna happen, you can first write the yc gonna be c1 plus c2x, because it's a repetition, gonna be e to the 2x. Now you can see that you can, even though this is just e to the 2x, you have to have, you can just multiply by x because that's already there. You have to multiply by another x, so that means it's gonna be a x squared e to the 2x. We still need to find a, but that's how it looks like. So you can see you need that another x in there. Okay, so as the last one, let's try to do this one. E y double prime minus 6. No, let's go back to the same one, so then we don't want to write another characteristic equation. Let's go back to the original first one. So y prime minus 6 y equal, let's say 3x e to the 3x cosine 3x. It's a product, so we can write one by one, but still remember you don't want to write a coefficient for exponential term because it's going to carry over with the others. So let's use that argument. So that means your y gonna be c1 e to the negative 2x plus c2 e to the 3x, and then so you can see that here 3 and 3 match. Since 3 and 3 match, you need to write a exponential form here. So, so it's going to be quadratic, so that means it's going to be a x squared bx plus c. So this is going to take care of both at the same time. E to the 3x, we just write it like that, and then cosine sine. But when you write cosine sine, do you really need a coefficient for one of them? Actually, you can see that you can remove one of the coefficients because it's gonna still included in ABC. So I don't write a coefficient for one of them, but you still need to write a coefficient for the next one. So 3x, but I don't write for cosine, but I write for sine. You just pick one. Good. So that means you only need 4 unknown for this problem, just 4 unknown. So that is the that is how the general solution looks like. Good. But remember, when you want to find the particular solution, you just find the particular solution first. No, you just find the particular solution separately and then you add it to this one. Otherwise, taking derivatives is like too much, it's taking too much time, so we don't do that. Okay, so let's do one more. So I'm going to give you a problem for you to write the forms. Good. So the example, so write the form write the form of yp for Ly equal ft, let's say t now, where the first one ft equal e to the 7t plus 6. We assume that 7 is not a root of the characteristic equation, so we assume that 7 is not a root. Okay? So it's a general case. Good. So what is the yp looks like in this case? So yp gonna be a e7t plus, oh, there's a 6, that's a constant, so we just put a b and then we try to find that. The next one, ft equal, let's say t squared cosine t minus sine t, like that. So t squared, that is a polynomial of degree 2. So what you can do is you can say a t squared plus b t plus c, and then you also notice that cosine and sine is the same number inside, is 1 1. So that means you can combine both them into 1, so you can just write, you don't need the coefficient for one of them because it's already included, so you can just write cosine t plus, but you need the other one, you need only one of them. It doesn't matter which one you're going to put, just put to one of them, so it's going to take care of both. You can make it worse, just writing 2, and but you don't want to do that. You can just combine. It's going to carry it's going to take care of both of them at the same time because they are same number. Okay, number C, ft equal 3 e to the 5t plus sine t plus t e 4t. Okay, so let's write the form separately. We assume that this 4 is not a root. That's the big assumption. So it is. So what we can do? So the first one gonna take care of e to the 5t. The sine one can take care of writing sine cosine. So b sine t plus c cosine t, and then for the next one there's a t. That means you have to write the degree 1 polynomial. That means it is dt plus e times e to the 4t. You don't write another coefficient for that because that's already there. So that is the form for that. And let's do d, e, yeah, d. ft equal t squared e to the 2t plus sine 2t minus 2 times cosine 3t. Okay, you can see that 2t and 3t are different. That means you have to write 4 terms there, 2 for that, 2 for this, because they are not the same. So let's write the solution for this. Yp equal, this is a degree 2 polynomial. That means a t squared bt plus c times e to the 2t and again we assume that 2 is not a root of the characteristic polynomial. Now for sine, you can write d sine 2t e cosine 2t, and then for the next one you can write f sine 3t g cosine 3t. So there are a lot of unknown here. Okay, that's a form. Good. And then I'm going to give you actually, for example, you can actually do the last one and tell me what you get. So I'm going to give you the solution for that. So let's, it can take some time, but you can try it. So this is an exercise. Find yp of the differential equation y double prime minus 4y prime minus 12y equal 3e 5t plus sine 2t plus te 4t. So I'm going to give you the answer that you get. You should get yp equal negative 3 over 7 e to the 5t. That's the first answer we get. And then 140 cosine 2t minus 1 over 20 sine 2t minus 1 over 36 3t plus 1 e to the 4t. Okay, that's what you get. So what do? You equate coefficient of linear independent terms. Okay, so equate. That's how you get it. Equating coefficients. Equating coefficients of linearly independent terms. Good. But this is just because you try to solve these kind of problems in your other things. But this is really not gonna happen in exams or quizzes or things like that, because it's very difficult. But you kind of know how to do it in case you want it. Now I'm gonna stop with the question. So the question is this. Find a particular solution find a particular solution of y double prime minus y prime minus 6y equal tan x. So if you try to do this problem using the same technique, it's not going to work, because we know that the undetermined coefficient method works for only 3 cases. It's the exponential, sine, cosine, or the polynomials. But we have tan x, so that means we need a new technique. So we can use what we call the variation of parameters technique. So we need a new technique. So we're going to say we cannot do this using this method. Okay, so need a new technique called variation of parameters method. Variation of parameters. Variation of parameters method. That we discuss in a different lecture. So we call variation of parameters method. Okay, so that's can handle little larger class like these kind of functions. Okay, so as the final thing, what I wanna do is I'm going to say that this technique actually work in general for even for higher order differential equations. So let's talk about that. So let's say this one. So I'm going to say our method works for higher order differential equation as well. Higher order differential equation as well. So let's do an example just to show you. So let's say find the particular solution of find a particular solution of so let's say y triple prime minus 3y prime plus 2y equal ft, where a ft equal 3e 2t, b ft equal 5e negative 2t, and then c ft equal negative e to the t, and the d equal ft e to the 2t e to the negative 2t, and then e to the t. Just add all of them. So so if you get a problem like that, what we normally do is look at the characteristic equation. So what's the characteristic equation? So the characteristic equation is lambda 3 minus 3 lambda plus 2 equals 0. Now the question is how to find the how to factor this. So the grouping method does not work. So since the grouping method does not work, so what we can do, we can use the factor theorem. But you can see that in the factor theorem, what do you want to do? You plug in some values, and if you get a 0, the lambda minus that value is a factor. For example, you can see that if you look at these numbers, if you plug in lambda equal 1, you're going to get 0. That means lambda minus 1 is a 0. Okay, so you can see that lambda minus 1 is a factor. Okay, because when you plug in lambda equal 1, if you plug in wherever lambda, if you plug in 1, it gets 0. That means by the factor theorem, lambda minus 1 is a factor. So you can see that lambda minus 1 is a factor. To find other factors, what I'm going to do, I'm going to use a synthetic division. So use a synthetic division. So how to use the synthetic division? You can write the coefficients. So what are the coefficients? You can see that these are 1, and then you have 0, and then negative 3 and 2. So those are the coefficients. So what we can do, we can divide this by, we know that the root is 1 here, so lambda minus 1, so the root is 1, so we're gonna go with 1. So what we do, we're gonna bring 1 down here first, and then you're gonna multiply and add. So when you multiply 1 and 1, you get 1. When you add, you get 1. Then you're gonna multiply 1 with 1. So what do you do? You multiply and add. First you multiply these two. That's a multiplication. That's exactly gonna go there, and then you're gonna add these two. It's gonna go down. Okay, so you multiply and add, multiply and add. So let's do that. Let's continue. So that means, and then you're gonna multiply 1 with 1, you get 1. You can add, you get negative 2, and then you multiply 1 with negative 2, so you can add 0. Perfect. You have to get 0 because it's a factor. You should get 0. Getting 0 means it's a factor. That means this can give it the other factor. So what's the other factor is lambda squared plus lambda minus 2, because there are 3 terms, so that's the other one. So now we can find the factor of the of this one. So that means we have lambda minus 1, lambda squared plus lambda minus 2 equals 0. So you can find factors. This is easy to find factors. So this is lambda plus 2 lambda minus 1. So that means all the roots are negative 2, 1, 1. Okay, so there's a repetition here. So now we can start writing the answer for this. So the answer gonna be for this one is yp. So this is 2 is not equal to, that means it is Ae to t. The second one is negative 2, that's gonna match. Since it's match, you have to add an extra t, so it is a t e to the negative 2t. The second one, you can see this is the repetition. When there's a repetition, your yc is going to be c1 plus c2t. That means you need another t when you write the solution, because this one and this one match. This match with that. So you have to be careful. So that means your solution is yp equal a t squared e to the t. And then the last one, yp is, you can see they have all the types, so we can write different one for each. So that means it is a e to t, b t e negative 2t plus c t squared e to the t. Okay. So yeah, so this is like, I'm just showing you how to do like higher order differential equations, but that's not a major focus in this course. But I want to tell you, like, we can still use the same technique for higher order differential equations as well. Okay, so this is the end of what we call the undetermined coefficient method. This is one of the major technique when solving non-homogeneous second order or higher order differential equations. But still, we can only solve 3 different types under this technique. If you get anything else, then you have to use some other techniques. One of the other technique is what we call the variation of parameters method. We can discuss that in another lecture. Thank you.